Okay. Uh, Today we are witnessing the fourth revolution in the domain of lighting technology. The very first light source, if I want to say lighting 1.0, was fire. Then lighting 2.0 is electrical light. And lighting 3.0 is LEDs, and lighting 4.0 is smart lighting. Okay, well, let's start from the beginning. Our friendly caveman here, Neanderthal or Homo sapiens, I don't know. Well, he needs light. He needs to create light. And in fact, at that time, we are speaking about prehistory. We know that prehistoric people, mainly Homo sapiens, but most probably not only, they discover the two single ways that matter has to produce light. Since then, we don't discover anything new. We just use technology. Well, the first one is the incandescence. Most probably starts with a spontaneous forest fire, and our caveman discovered the hot way to produce light. Hot way means what? If I inject energy to the system, very few % of that energy is produced, is turned to light, and the remaining is heat. Very inefficient. Of course, the first thing to use is fire. And we have proofs, I don't say historical proofs because we are in the prehistory, we have proofs that humans dissociate the lighting power of the fire from all other activities since at least 30,000 years before today. How we know that? In prehistoric caves with paintings that we can give a date thanks to carbon-14 that are from minus 25,000. They are stalagmites, you know, the lower part, stalactites from above stalagmites, cutted and with a hole in the middle, and inside sometimes we found trace of animal or vegetable grease. It was clearly that stalagmites serve as torches, and if you put fire on that place, you can see all the paintings and the shadows finish the paintings, and as also the fire move, you have the first cartoon of the humanity. You have the feeling that the paintings are moving. Well, 30,000 years, human beings use fire to generate light, not anything else. Then, of course, from fixed torches, here create moving torches. You take a part of wooden, you put the grease, and you can move, okay, or bones. Then we arrive in historical areas. Candles. Candle is a moving torch, but you use a mesh to a vegetable mesh to burn, plus what is the name that the bees produce? Sorry. Yeah. And then you have the comburant. Then you go to oil lamps, gas lamps. Gas lamps is 19th century. And that's all. The history stopped here. Nothing more since the beginning of 19th century. From the other side, our guy here discovered also the cold way to generate light, the luminescence. Cold means if I input energy in the system, the biggest part of the energy will be light coming out. and the remaining will be heat. That means much more efficient than all that. What was the luminescent sources that he knows? Bioluminescence, fireflies, luminescent mushrooms, or some animals in the seas, and things like that. Very difficult to use, of course. Phosphorescent minerals, but phosphorescent minerals was very difficult to find, not very easy to use for producing light. It was more symbols of power, like if you have seen the Lord of Rings, the famous Arkenstone, the luminescent paper of there is. It was not to produce light, but it was the stone of the king. Tribo and thermoluminescence, what means that? Some materials, when you scratch it, tribo, in Greek, they may become luminescent. And when you heat them, before become incandescent, they can produce a lot of light using that we call today candoluminescence. But all these materials are very difficult to find and use. And of course, he knew lightning, not lighting, lightning. And also for him that was a god and not a way to produce lighting. Well, he understood very rapidly that beyond to find a lot of fireflies, this kind of source is not very easy to dump and use for lighting up his caverns, his homes, and whatever you want. Just for fun, Japanese people during Edo period, that means the middle age in Japan, but this is in springtime, that they go to collect fireflies in the forest, and they put the fireflies in lamps with rice paper around, and they use the fireflies to light up some parties outside, some festivities. But okay, humans, they had a dream. Someone told us, I had a dream. Yeah, this one also. He wanted to be able to catch lightning, put it in a bottle, and produce light. Very nice dream, isn't it? Huh? Yeah, but we make it. Thanks to the electricity. Thanks to electricity ferry. Well, the very first electrical lamp operating in our world was not a incandescent lamp. It was a lamp using electric discharge, which is a luminescent process. It's the cold way to generate light. And this lamp has been produced by Sir Humphrey Davy in UK, and his disciple was Faraday. Well, Davy, in fact, doesn't try to create light. Davy is known for some special lamps for people working in mines in order to avoid explosions. But this is not was his objective here. The objective of Davy was to prove the theory of Franklin that lightning is an electrical phenomenon. You know Franklin with his thing flying, don't know the English name, cerf-volant, I don't know what this is. He proved that, he said that lightning is most probably electrical phenomenon. And Davy said, if we want to prove this phenomenon, we have to reproduce the phenomenon in the laboratory. And what he made, he took two electrodes, two carbon pieces, connected to the only available electrical sources at that moment, that was the volta element. And he said, okay, let's see what will happen. Do I have a lightning between the two electrodes? Problem is, today we know that if we want to achieve sparking, we need in free air to put 30,000 volts per centimeter. Davy was obstinate, and he put, following the papers, in series up to 4,500 elements of, 3,000 elements of Volta battery. That means 4,500 volts. But even like that, he was very far from the value, and he didn't see anything. But he was convinced that Franklin is correct. And at that moment, we're speaking about 19th century, okay? No one knows what was atoms. No one had the knowledge that we have today, and possible physically to understand what happened. But they had a very good knowledge of that we call similarity rules. And then Davy said, okay, the phenomenon that Franklin observed as this electrical phenomenon happens at a very long distance in atmospheric pressure. I'm trying to reproduce in very small distance. Well, if I want to have similar conditions, I needed to lower the pressure. And he put the two electrodes inside a recipient that we call today the eggs, the Davis egg. You can see a copy in the Museum of Science in London, and he start extracting the air, and he make the right hypothesis, because we know today when you lower the pressure is, you arrive to a breakdown minimum, and then you increase again, but this is another problem. And in fact, with 4,500 volts and a little bit less pressure, he see the sparking. He was very happy. Franklin is correct, but his student Faraday observed that this thing produce light and stable light. And he started exchanging letters with other scientists. And in 1813, we have the first carbon arc lamps proposed by Faraday. One of those lamps has been installed to a lighthouse, marine lighthouse in south of Cornwall. And this lighthouse, we have writings that says that this lighthouse was visible from Calais, from the French coast. And we could estimate what was the luminance, the brightness, and the flux of this lamp. And we could estimate that the efficacy was in the order of 10 to 12 lumens per watt. Rather good efficacy. Well, the problem is that this technology was very innovative and complex. You need a lot of power, high voltage. The lifetime is not good because the electrodes by carbon are eroded. And if the electrodes are eroded, the distance increase. And if the distance increase, the voltage to maintain the spark should increase, and this is complicated. And for that, they introduce some complexity. Here you cannot see it very good. It's a photocopy of an image of such lamp that I got from a journal from 1840, something like that. And here inside you have a full mechanism with counterweights that use the repulsion between the electrodes, the electrostatic force, to equilibrate the distance and keep the same distance between the electrodes. This is the very first closed control loop in the world, and maintains the electrodes in fixed distance. But even like that, the electrode erosion was so fast, you need to change the electrodes almost every week or every day. And of course, you have reliability problems. And we had to wait 1870. This guy, a Russian living in Paris, in France, he proposed that we call today the Yablukov candle. That was a lamp using the arc principle from Faraday, that was stable, easy to use. The only problem is you have to have what? Electricity. Okay? And, well, the idea were there. We used those lamps to illuminate the very first universal exposition in Paris. All lighting technologies, the very first examples have been demonstrated in a universal expos. And then you have our friend Edison, 1878, who used the incandescence, that means the hot way, to generate light. In fact, Edison doesn't discover anything. Edison bought a patent from a Canadian team, and this Canadian team was telling that you can generate light from incandescent material and harness that. And all scientists at that moment was telling, haha, what they are telling is stupid things. You will never get light from that. And Edison believed them, bought the patent, and just make the first commercial lamp. In fact, Edison's lamp has a main drawback. The main drawback is the use of incandescence. That means very low efficacy. Mind you, Faraday lamp, 10 to 15 lumen per watt. Here we speak about 1 lumen per watt. 10 times less efficient, but mid of 19th century, who was caring about energy efficiency? Who was thinking that the resources of our planet are limited? No. But his invention has a number of strong points compared to the other lamp. The first one is easy to make. What is Edison lamp? Or, well, that we call today Edison lamp, is a filament. Initially was made by carbonized bamboo. Mr. Philips in Netherlands does the same thing by using carbonized cotton, cellulose, who made it himself, that's okay. A bulb, that because we still call the lamps bulbs. Primary vacuum, in order to avoid to have oxygen and consume the filament when it's very hot. 2 connectors, few wires, and you can produce in series, and you can sell that. No problem. And the lifetime also. I remind you that Faraday lamps, you have to change the electrodes almost every week. Here, the very first versions of Edison lamp had at least 500 hours of lifetime. Even today, when we have a lamp at home and we keep it on, we never use it more than 1,200 hours per year. In rooms like here, we use the lamps for around 4,000 hours per year. 500 hours there was infinity. But that was not the main reasons why we completely forgot discharge lamp, and also people, when you ask what is the first electric lamp, will tell you Edison. Why? In fact, the big difference is himself. Edison was a real envisioning person. We can see person like him once every 100 years. We can speak similar about Newton a few years before him, and maybe our days, Steve Jobs could be entering the same category. But Edison said, okay, I can produce lamps. People need lamps to light up because it's a fundamental need. But if you want to sell lamps, people have to use them. And to use them, they need electricity. Well, then he started producing electricity at centralized areas. He used initially the Niagara Falls because it was not very far from his place, and distribute electricity, and that make the possibility to people to buy his lamps. When we start to illuminate our homes, end of 19th century, it was not any other electrical appliance but lamps. And that was the idea of Edison, and this idea made birth to that. Do you recognize the signal, the signal? GE, General Edison, that became later General Electrics, and this is the biggest worldwide industrial group ever done in the earth. Lamps are at the origin of General Electrics. Philips, Royal Philips, also starts with lamps. Osram in Germany starts with lamps. Today, neither GE nor Osram nor Philips, they are making lamps. They spin off their parts and they sell it, and they are plus or minus independent, but they completely changed name. But three mastodons of world industry, they are coming from lamps, and just for the need that we need to create artificial light for our homes. From those two lamps, two technologies, many things happen, not so many in the incandescent part, starting from Edison lamp. Edison replaced the carbon filament with a tungsten filament that allows to have higher temperature before melting and produce more light. Even you can spiral the filament several times in 3D and compact the filament inside the lamp. Around 1980s, we needed to 980s, 100 years later, we needed to increase the efficacy of the lamps in order to avoid the first oil crisis, and people include some halides inside in order to make the filament hotter and protect the filament against destruction. This is the halogen lamp. Then later in 2000 we speak about halogen high efficacy, and also beginning of 90s, we had outside of the bulb reflective coatings that keep the infrared inside the lamp and leave the visible part of the radiation to come out, keep the lights out, and keeping the infrared inside the lamp. You can focus it on the filament, and you can increase the temperature of the filament without using additional current. Okay, that was the idea. But this is all here. From the other side, the luminescence, starting from Yablukov's candle, many things happen. It's difficult to say such kind of evolution here. If you take discharge lamps, you can have lamps that they have a continuous spectrum. You can have lamps that they have atomic spectrum lines. You can have lamps that they have molecular spectrum. You can have atoms, molecules, or very dense plasmas emitting radiation. The operational pressure inside the bulb can go from a few hundredths of atmospheric pressure. If you take a fluorescent bulb and you crush it, it implodes because the pressure inside is 1/500 times the atmospheric pressure. The yellow sodium lamps that illuminate our cities, you are in around 2 to 3 bars, 2 or 3 times the operating. Vapor inside, the pressure can reach 400 bars in a few millimeters cube volume. And also the way that you input the power change a lot. You can use AC, you cannot use DC. Discharge lamps, they don't accept DC, it's not possible. You have to use always AC, but you can use AC at 50 or 60 hertz. You can use AC at 1 kilohertz, 2 kilohertz, maybe 20 or 100 kilohertz, no problem. You can go even to megahertz. But this assumes that you have electrodes inside the bulb. But you can even get out the electrodes, use just a bulb, and inject the power thanks to capacitive or inductive coupling. Or even you can, we have lamps that they inject the power using microwaves. You know very well, if you take an old lamp, I don't advise you to do the experiment with any kind of microwave oven. If you put the lamp inside the microwave, the lamp will light up. And between those two, you have the cluster lamp, which is something very specific. It was demonstrated in the last year of last days of 20th century. It's a lamp which is a discharge lamp but emitting incandescent spectrum, continuous spectrum, and never had any commercial application. However, here in the domain of luminescence, a revolution happened. This revolution is the solid state lighting, and this afternoon we speak exclusively about solid state lighting. I'm speaking about LEDs, light emitting diodes, or organic light emitting diodes, plastic foils emitting light, and also some other more exotic devices like field emission. Only evolutions here, evolution and revolution there. Some definitions about light sources, very important, and here we speak about color temperature, color rendering, because this part is not something generic, it's linked to the lamp. Well, first thing, we speak yesterday about radiometric and photometric quantities. There is the same here. There is a difference when we speak about efficiency and efficacy. Okay? Efficiency is the radiative power divided by the electrical input power. You have the definition here. A linear fluorescent lamps T5 can go up to 25%, okay? Which is very nice. An incandescent lamp doesn't exceed 5%, which is very bad. And white LEDs can go up to 30 to 40%. Yeah. Sorry? You will understand. Fluorescent is the bulbs. I don't know, maybe here there is one behind, you know, the tubes. And the incandescent lamp is the bulb that we have with the filament inside. Okay? This is, we will speak about that after. And white LEDs, you know what is also in that case. Look, this is the problem. In fact, if you take an old kind bulb, 100 watt incandescent lamp, finally only 2 watts will be used to light up your home. All the remaining is losses somewhere in the global system, and the remaining 98% here also will be radiated as infrared. And if you are in India, if you radiate heat, then you have to evacuate the heat by using air conditioning, which is more powerful for the air conditioning than before. This is the reason why we ban incandescent lamps, because they are very inefficient. But for someone working for lighting, this parameter here is not interesting. We are speaking in photometric units, which is the efficacy, the luminous efficacy in lumen per watt. That means luminous flux in lumen over input power in watt. You can see that the definition difference here is the integral of the spectrum from 0 to infinity, including infrared, UV, that is not used for lighting. Here you integrate from 360 to 780, only in the light, and you ponderate with the V of lambda function, the response of the human eye, plus the 683 in the front. And then look, an incandescent lamp, the old lamps, 12 to 14 lumen per watt. A halogen lamp, which is came around 1990, 20 to 25, this is the best that we can do with incandescence. Low energy lamps, this is the compact fluorescent lamps, in fact, can go around 65 lumen per watt. A linear fluorescent lamp, the small one, can go up to 110. Metal halide lamps for the cities up to 150. Low pressure sodium, very yellow lamps, they almost disappear now, 200, but you will see the difference after. LED filament lamp, the new lamps, the very last one, are more than 210 lumen per watt. And the Firefly, the real Firefly, 180 lumen per watt. That means before 2019, that we had the LED filament lamp, all other technological lamps beyond the sodium was less efficient than the Firefly. How you can measure that? You can calculate how much the Firefly eat, how many kilocalories, and then you put the Fireflies in an integrating sphere, and you measure the light that it produces, and you make a ratio. There are some colleagues that play with Fireflies, and they make that calculation. Second parameter interesting to know is the color temperature. The color temperature reflects the object that absorb all the radiation that emits itself. Black bodies, the only real black bodies that we know in our world, they are the nucleus of the stars. Okay, in Earth we cannot have a real black body, but you can imagine the black body like a cannon bullet, which is hollow, and you drill a very small hole, you hit the bullet, and you look from the small hole what is the color of the light coming out. Okay, small hole to not perturbate the system. And in fact, if we simplify, if I take an iron bar, if I start heating the iron bar at 1500 Kelvin, it will be reddish. If I continue heating more, 3500, the bar is theoretical, otherwise will melt. The color will be yellow-orange, and if I go up to 5000, the apparent color will be white, bluish. Okay, the bar is a theoretical bar. No one can resist at 5000 Kelvin and stay in the form of a bar. Sorry. And then we have here that we call the color temperature scale. And we say here we have hot, warm white. And here we have cold white. In fact, there is a problem. Source with less than from 5500 Kelvin and above here, we consider that is cold white. When we are lower than 3300 here, we call that warm white, and in between is neutral white. This is contradictory because the temperature of the black body is higher when the color is bluish, and we consider that as cold, and vice versa. In fact, this coming from our interpretation of the world. The water in a large quantity is blue. The ice also in large quantity is blue, it's bluish, and we attribute all blue shades as cold colors. But the fire is red, hot things they are red, and we don't go to touch, it's question of protection, and we consider that reddish, orange, yellow colors, they are considered to be red. This is unfortunately the only way that we have to measure the shade of the white light. But it is very problematic if people, they don't have the way to understand the problem. For incandescent lamps, all incandescent lamps, the color temperature goes around here, 2800, which is the temperature of the filament. And you have not to care because you buy always lamps here, warm white. With LEDs, you can have warm white neutral white, cold white. And you have to understand what is the difference. You will see later that there is important difference between warm and cold white light, especially in our well-being and health. We cannot use any kind of light for any kind of application. We have to understand that. And now imagine your grandparents or your parents. Tell him, if you buy that lamp, the temperature shown above is very high, but the color is cold. If you buy that one, the temperature is low, but the color is warm. And when they see 5,000 degrees, they tell you, wow, if I touch it, I will burn. No, the lamp is very cold. It's maybe 20 degrees C when it operates. Well, you see, it's very confusing. And what they do usually now in the stores, they have demonstration box. Push the button, look the color. I like that one. This is the value that you look in the box, and you go get your lamp. Otherwise, it's very difficult to explain. And for us as engineers and scientists, color temperature is very approximative. That we need to really use is that called the correlate color temperature. If you take the color triangle, you have seen that, all the colors are there, and in the middle of the triangle, you have the black body locus here with the different temperatures. And for example, if your color point for the lamp is here, then the color temperature, the correlate and proximal color temperature is 5,000, is 10,000, and so on. And a point somewhere here, the lamp is green lamp, is not white lamp anymore, and you cannot associate a color temperature. You have to not be very far from the black body locus in the color triangle in order to define the correlate color temperature. Color rendering index. How your lamp is renders the different colors. Okay? Color rendering index, ERC or RI, is a percentage going from 0 to 100. If you have 100, you have the maximum CRI, and that means your lamp produces an appearance of the color exactly the same with a reference white lamp. Not with a natural white, but you take a reference lamp, you measure the colors, and if you have CRI of 100, you say that this lamp produces the colors exactly the same way that the reference. And look here, and 0 of course means absence of recognizing colors, and our eye is a very special machine. You see that this morning. Just 5% variation is perceivable. Look here, if you take a lamp that has a very broad spectrum, this is the response of the eye. Is that what you see? Here we have a CRI of around 80. And if you take a sodium vapor lamp with very high efficacy, look here, no color anymore. CRI here is around 20 or even lower. And look also that street illuminate with yellow low pressure lights, low pressure sodium lamps. Look, this is a white car here, it's a yellow car, and this is a gray car. Do you see any difference? The problem is that these metrics, the CRI, not ERC, sorry, ERC is in French, CRI, the International Commission of Illumination, which is the standardizing body for lighting, exhorts since the beginning of that year to suppress CRI metrics and replace with something new. Other thing that is very important to understand when you have to use lamps is the famous lifespan. When you buy a lamp on the box, normally they tell you what but it's most probably on, off, on, off. It's at least 1 second between the on-offs. Well, what means that? If they gave you that the lamp will live for 15,000 hours, from the moment that you switch on the lamp from the beginning, the flux will reduce with the age of the lamp gradually till a limit value. Beyond that value, you consider that the lamp is dead, even if it continues to produce light. And this is the value that is marked on the box. But this is a value marked on the box if the lamp is supplied with exactly the right voltage, with pure sinusoidal way, with all the conditions that you can imagine for metrology. Now, if you are living in a remote area and instead of 230 volts, you have 180 volts at your home, most probably the lifetime of 15,000 hours will never be respected. But that will be a problem of the electronics, not of the lamps. Well, there is the exact definitions of the lifespan. There are two definitions of lifespan. This is that we call the economic and median lifespan, and they are they are illustrated with these symbols here. Normally, you can find those on the box of the lamp, or if the lamp has a QR code, you can find that by scanning the QR code. You can look that on the registration database. L here is the brightness, and B is the failure rate. If you have here L50, XX equal 50, that means the value that you have for that lamp, 15,000 hours, means that at 50,000 hours, you will reach 50% of the initial brightness, of the initial flux. And if here you have a B20, and only 20% of lamps in your area will fail. This gives you information about potential failures in that period and how much the flux will go down. Usually, for legacy lamps, discharge lamps, and incandescent lamps, we use the economic lifespan. And when you see for an incandescent lamp 1,000 hours or 1,200 hours, which is the usual duration of an incandescent lamp, that means at that duration you will have 50% of the initial flux and 50% of the lamps will be still on. It's always L50, B50. Now, for LEDs, the situation is different because we know that LEDs, or they will fail immediately within a couple of days, and this is a problem with the electronics, not with the LED, or is no more need necessary to add the failure rate behind, because we know that it will be always higher than lower, than 1%. Okay, we keep only the L, and this is the median lifespan. But for legacy lamps, the XX here is 50% of the initial value. For LEDs, we consider that the LED is dead when the flux is just 70% of the initial flux. That means if you have 100 lumens at time 0, marked on the box, when you achieve 70 lumens, you consider that your lamp is dead and you have to replace it. Why that? Because then after the decrease will be very rapid, and if you have here, I don't know how many lamps you have, it's better to change all of them at once than change lamp by lamp, because it costs much more money to move people to change lamp by lamp. You have to pay them for that, and this is especially true in Western countries. Well, this is the difference, is the way to read, and here is, you see, aging versus catastrophic failure, that I will explain you. You see, for that lamp, you start at 100% of the flux, and the flux is depreciating. The industry tells you can be between that and that. And for example, if I tell you 15,000 hours, that means 15,000 hours, that goes for a fluorescent lamp, is 50% of the initial flux. Here, 15,000 hours is 50% of the lamp still alive after 15,000 hours. And those curves here are given by the lamp manufacturer. We are speaking here for good manufacturers, but in fact, discharge lamps has been produced mainly by 3 big manufacturers, Osram, Philips, and GE, and a few Japanese, and then all the remaining was peanuts, and of course we can rely on what the 3 big manufacturers gave here. Okay, that's all about definitions. Now, do you want to make a short but very short break? Otherwise, I can speak you rapidly till 1:30 maximum about the legacy technologies. I will explain about incandescent lamps, fluorescent lamps, sodium lamps, and things like that. It's okay? We can go? And this afternoon, 3 to 4 or 4:30, we speak about LEDs. Okay, there is coming, yeah, there. Let's speak about legacy light sources. That means light sources that will disappear within the next decade maximum, or at least for general lighting. For some specific application, they will still there. And the first one, the famous incandescent lamp from Edison. Now you know very well what is an incandescent lamp. It's a bulb with a metallic filament, a current passing through, and the temperature of the filament increase, and the radiation produced by the filament, the light produced by the filament, is proportional of the power, fourth power of the filament temperature. The problem is that this lamp emits a lot of infrared. The maximum of the black body is somewhere here, that means in the infrared part. The infrared cannot be seen, but the infrared is radiating and heating. That means you have to evacuate the additional heat. This was used only for interior lighting, mainly general interior lighting, and can be supplied either in DC or AC. Doesn't make any difference. The spectrum is continuous. But due to the fact that I explained you, we decide since 2009, 2008 to ban this kind of lamps from worldwide markets. You see, the very first was Switzerland, Australia, then Europe, but Europe make the ban gradually, and then you have different other countries. India, you ban it at 2012. Now, today in Europe, 10 years later from the last phase of banning, it's almost impossible to find a incandescent lamp in the European market. What means ban the lamps? Means that you cannot anymore import, you cannot anymore produce inside the country. And if you as a consumer, you buy an incandescent lamp, say from Thailand, that they still have, you are considered to be importer from the law. And you may have sanctions. Well, they never look that if you buy 1 or 2 lamps. But the idea was here completely to make those lamps disappear. And also the law say that if you have a stock of lamps, if you have lamps in your storage, you can sell it till you exhaust the stock. Okay? That was not forbidden. And what happened, for example, in Switzerland, when Swiss people learned that their government banned the lamp, they go to buy all the lamps that they found in the market, And immediately all the lamps disappear from the market, but the people keep the lamps at home. And as those lamps, they have a life of 1 year, 5 or 6 years later, no more lamps in the market and in the homes. And breaking news, February 25, 2022, 2 years ago, Europe decided in advance of phase to ban all other discharge lamps containing mercury. Not because of the efficacy. Some of those lamps, they are very efficient, not a problem, especially fluorescent lamps, but mainly because they contain mercury. Mercury is toxic element, is very bad for our health. Normally we have to recycle the lamps. In Europe we recycle maybe 30% of the lamps, which is nice but not enough. And we decide completely ban from that date all the other lamps. They gave some grace period to the different technologies. For example, for fluorescent lamps, they gave a grace period of 3 or 4 years before the rule apply. That means next year it will be no more possible to import or produce fluorescent lamps in Europe. And that means if you take into account the stocks, most probably fluorescent lamps in 3 years, say by the end of the decade, it will be not more possible to find fluorescent lamp or compact fluorescent lamps. It's the same thing. And it's more funny because this is linked to the Minamata Convention on Mercury, which is an international convention. And this convention has been signed not only by Europe and some other countries, but it's also signed by a lot of African countries. For them it's not a problem because they don't produce any kind of lamp, but they are very aware about the fact the lamps that they came there with mercury inside, they finish as trash outside, and the mercury is very bad for the environment. Okay, there is the family of discharge lamps. We don't speak anymore about incandescent lamps. Discharge lamps, we have two big families, one with electrodes. You have metallic parts inside the bulb to pass the current through an electrical discharge, and electrodeless lamps, with electrodes and electrodes. With electrodes, we have low pressure, pressure lower than the atmospheric pressure, or high pressure, pressure above the atmospheric pressure. And here you have different kinds. We'll speak about some of those, not all. The first one that is still there and is one of the most efficient lamp in that family is the fluorescent tube. In my country we call also very often neon, but you don't have inside any neon. You have mercury, argon, and krypton in some case. You never have neon inside. But the familiar name is neon. I don't know how you call here in India, but maybe it's the case here. Well, and you have different kinds. You see here the codes T12, T8, T5. You understand what is just after. You can have any length. You can have linear. You can have U-tubes. You can have round tubes. Everything is possible. And you can see here the luminous efficacy. Here is low, between 40 and 65. And in T5 tubes, the smaller one, you can go up to 110, 120 lumen per watt. And in fact, like a incandescent lamp was been, thanks to the power, 100 watt, 60 watt, 75, 60, 40, 20, and nothing in between. Those one, they are been with the length. You cannot find in between, or is very special. And the length is proportional to the input power, because the length of the discharge is directly linked to the power that the discharge absorbs. Lifespan, For the old one, 6,000 hours. Those one can go up to 20,000 hours. That means in buildings like that, we use the lamps 4,000 hours per year. You need mainly to relamp or your building every 5 years. There is the spectrum of those lamps. You can see here, but if you look the spectrum with a spectroscope, you will see just few atomic lines where are the spectrum of mercury, and mercury has a very poor spectrum. That means this kind of lamp cannot really reproduce colors. If you don't use chemical materials that we call phosphors, there is no phosphor inside. Phosphor is luminescent materials that they catch UV radiation emitted by mercury. Because mercury emits radiation here, you cannot see it, of course, and this radiation is caught by the powder, the luminescent powder, the white powder that you see in the tube, and is transformed in additional light here. And the old generation of lamp, they had a very poor color rendering index, below 80. The new generation can go up to 90, which is very good. And for special applications, we can go up to 98, which is excellent. Special applications is, for example, selling vegetables or fruits, because you need to see the right color, or selling meat, something like that. We can achieve any color temperature from 6,000 cool white up to very warm white, 2,800 Kelvin. It's just playing with the chemistry of the powder of the phosphor. Well, I spoke to you about T8, T12, T5. What is this Kabbalistic code? It's very simple. T8 means 12/8 of inch diameter of the lamp. And if you take 12/8 of the inch, you will find that the diameter of that tube, the older one, is 38 millimeters. Why we speak in that unit? Because it has been standardized by the Americans, and all people took the designation T, T12, T5, T8. Okay? And look here, the evolution of the technology. Beginning of 50s, we have only the T12 lamps with luminous efficacy up to 60 lumen per watt, working only with ferromagnetic ballast, big adapters behind in order to stabilize the current, because the lamp is working in current, has to be driven in current, not in voltage. When we speak tomorrow about drivers, I will explain you that. And the powder was a very poor quality powders made on hollow phosphate, and this product is obsolete and is not recyclable. In fact, we can recycle it, but we just take off the mercury, and the remaining part we put it in concrete, and we keep it for centuries in order to avoid that pollutes the environment. Is not economically a good idea to recycle those lamps. Then the second one was the 26 millimeters, the T8. You see here you go up to 95 lumen per watt. They can operate for the first generation with the old ballast. That means you can get out a T12 lamp and put a T5 in the place, in the same fixture. It works. But since 90s, Europe banned the ferromagnetic ballast for interior lighting, and we passed to full electronic ballast, electronic drivers, if you want to use that term, inside the fixture. We passed from hollow phosphide to 3 phosphors, much better phosphor, more efficient, and much more expensive. And in that case, you can recycle, you can recover the phosphors, because economically speaking, you can have some benefit if you recover the phosphor and you resell it. And finally, the last generation, the T5, 16 millimeters, up to 105 lumen per watt. It operates only with electronic ballast and has only 3 phosphors. that is fully recyclable. Up to 90% of the material inside those lamps can be recycled and reused. Yeah, there is the coding. I spoke to you about the diameter, okay? And there is the code that you will find on the top of such lamps. It's always written in the lamp. Even if you don't have the box, you can know exactly what lamp you have there, because you have a code of this type. In the front you have F. It may be absent. F means fluorescent, and now we don't put anymore because it is fluorescent. Some years ago, some decades ago, it was also sodium lamps with the same appearance, and they had S in the front. Then the two figures here is the power. This is a 32 watt lamp. T is a tube. If it is a round lamp, it's O. If it is a U lamp, it's U. It gives you what is the shape of the lamp. 8 is the dimension. Calculate in 1/8 of inch. Okay? And then you have 3 other figures here that give you the color rendering and the correlate color temperature. The first one is the color rendering divided by 10 and trunked. That means this lamp has a color rendering index of 70, between 70 and 79. Because 70 or 79 divided by 10 equals 7, you cut the decimal points and you have only 7 here, and the 35 here is the correlate temperature divided by 100 and trunked. That means this is a 3500 Kelvin lamp, which is almost warm white. Okay, it's neutral warm white. And then you have other markings behind that they are specific to different industries, and you have to look in the catalog of the industry that they explain you what are the figures here. But the power, that the T something, and the 3 numbers here, they are always present in serigraphy on the top of the lamps. There is the way that the lamp operates. You have a tube. You have inside electrodes. You send a current. The problem is that you feed the lamp in a voltage, AC, and the lamp needs 400 milliamps usually, AC current to operate. And the only way to transform a voltage source to a current source is to put in between a driver, a ballast. We call that a ballast. Initially, the standardized name was ballast. The driver is now standardized for LEDs. This is a ballast, and the most easiest way, Thevenin and Norton law, if you put in series a very big inductance or impedance, you transform that in current source, and this is okay, you stabilize the current. When the current arrives here, what happens, first of all, hits the electrodes, and the electrodes start emitting electrons, and the electrons will accelerate thanks to the voltage here, the voltage drop, electric field. The electrons accelerate, they make collision with mercury, and then ionize mercury, and the discharge is established under some conditions, and then the mercury get energy thanks to collisions with electrons. The electrons get energy from the field from the plug, and so on. And the mercury excite, as I explained yesterday, and de-excite, but the main de-excitation of mercury here is in UV and even UVC. Mercury emits mainly at 254 nanometers, which is very dangerous radiation for humans. But this radiation will come here, 24 watts, will be catched by the fluorescent powder, the phosphor, and will be transformed to light, visible light. And finally, if you make the sum of the different losses, in a 40 watt lamp, 10 watt is light, and 30 watts is still heat, is 25%. But 25% for an electrotechnical system is very good. I'm speaking only about the lamp. Incandescent lamp was 2%. You see the difference. Problem. That lamp doesn't like cold outside temperatures because the quantity of mercury inside the tube depends on the tube temperature, which is an equilibrium between the outside temperature and all the exchange of the power with the lamp itself. And when you have a lot of mercury present, the mercury has a problem, reabsorb his own radiation. And he reabsorbs his own radiation, you increase the losses. And then initially when you increase the vapor pressure of mercury, you increase the radiation, and when you have a lot of mercury, the radiation decline again. The optimum operating temperature for lamps is around 25 degrees C, ambient temperature, that you can find usually inside a room. If you go outside, here is very hot. If you go to my country in the winter time, it's very cold. When it is very cold, I have very few mercury, and not only I have very few light, but the lamp asks also for more power. That means the efficacy is even worse. This kind of lamps, we use them only for interior lighting. It's absolutely meaningless to put them outside, except if we are in some areas that the temperature stay all year around 25 degrees C. A variation of that lamp is the compact fluorescent lamp. The compact fluorescent lamp was an answer to just be able to replace incandescent lamp. Is plug and play. You have the same socket with a screw or any other kind of socket. You have the tube here, which is smaller and has been bent to give smaller size. And inside the part of the lamp behind, you have a very simple power supply. Usually it's a half H bridge resonating system that allows the lamp to operate and transform AC voltage to AC current to the other side, but at a higher frequency. We are speaking here about frequencies of around 20 kilohertz. Okay, you can have here some information. The power source lamps can go between 8 and 80 watts. The efficiency when the lamps entered the market was very good. 65 lumen per watt was excellent, 5 times higher than the incandescents. Okay, and comparable to classic fluorescent lamps. But since then, never increased a lot. Lifespan between 6,000 and 12,000 hours. This is also okay. CRI between 70 and 90, depends what you put as phosphors. Correlate color temperature between warm white and neutral white, but very low startup time. When you switch on, you have to wait 5 minutes to get all the light. And if you put that lamp in the restrooms, you enter, you switch on, or a detector switch on the light. The time to get all the light, you finish, you go out, you switch the lamp, and then if you switch on and off, you will destroy the electronics behind, not the lamp itself, but if the electronics is out of order, the lamp is not operating. This was recommended for indoor lighting, and it is also banned in Europe, but still we can use it for a couple of years more. We ban it because it is supposed to not be anymore in agreement with the European directive RoHS, which is the directive for harmful materials inside the system. Mercury, it is fully recyclable. 96% of the material can be recycled. And of course, it is forbidden to put on the bin. You have to get it in the market. They have special bins, and every month or every 2 months, a national organism collect the bins and recycle the lamps. Okay, this is happening usually in Europe and some other countries. And when you buy a lamp like that, in Europe you pay 50 cents more. It is marked, that we call the eco contribution. You pay the moment that you buy the lamp, the recycling of the lamp. That is the reason you can return the lamp in the bin without to have to pay anything, because you pay the return when you bought the lamp. And this is valid not only for lamps, but any electrical material. Kinds of compact fluorescent lamps. This is the plug and play for general consumers with different shapes, different sockets. And this is for professional use. You see here is pin-based. You don't have any more sockets. You don't have any more power supplies and ballast inside. But this kind of lamp is made to be plugged in a fixture, and the fixture contain the ballast. And this one is usually used by professionals. This one is for general public. A variation of that lamp is the induction lamp. Here is electrodeless. The first induction lamp has been proposed by Philips, was the Master QL lamp. What is the idea here? You have a bulb that you can see here with a hole in the middle. The bulb is, let me show, I think I have another image, but I will show you later. The bulb is the external, and the thing that you see here, the figure, is closed, and inside the hole you put this RF radio frequency antenna, and in fact the antenna sends electromagnetic waves, and these electromagnetic waves excite the gas, create a plasma, and in fact you have a transformer, which is the primary is the antenna, and the secondary is one wire, one loop plasma. Inside you have mercury, argon, and maybe some krypton. It's like a fluorescent lamp. You can see here the powers up to 165 watt, good CRIs, variable color temperatures, but huge lifetime, more than 100,000 hours, because the sensitive parts of fluorescent or compact fluorescent lamps are either the electronics, but especially the electrodes. The first thing that fails in in a fluorescent lamp are the electrodes. Here, no electrodes, no more failures. But electromagnetic radiation problem, health problems. This is because Philips initially, when bought that lamp, incorporate inside the fluorescent powder, inside the phosphor, some iron particles in order to make a Faraday cage and avoid that the radio frequencies goes beyond the lamp, because you may have health problems. Some evolution, the Philips one, and then General Electric also produced another type of lamp, the Andura, that you see has a different shape. The electrodes inside to be inside, they are outside, they are here, and the guy who invented the lamp, this lamp, I know him. He called that lamp the bagel tokamak lamp, because it operates the same principle like a tokamak and has the shape of a bagel. There is the way that the lamps operate. The first one, the antenna is inside, and you have the field that couples with the plasma, and as I told you, you can assimilate the lamp to a transformer with a single secondary wire, which is the plasma, and the current turns around the antenna. Here is different. The current is flowing inside the tube and is perpendicular to the antenna, but it's the same thing. It's like a transformer. Well, this kind of lamps, they contain mercury, and also they have electromagnetic wave problems. They completely disappear. But the problem is that when you read the European directive, before speaking about mercury, this lamps has been ignored for a long time by European legislation, and that allows people to continue selling those lamps. Now with the mercury, these lamps also, they are completely banned, and the problem disappear. This is the famous low pressure sodium lamp. It's a big lamp. It was used to eliminate usually highways, or eliminate also cities in UK, or highways in Belgium. It's very interesting because it produces a single line, sodium line. You know, if you take salt and you put salt in the flame, gas flame, you see yellow light coming out. This is exactly this radiation is the response of sodium when it is excited, and the flame can excite the sodium. Is enough hot for that. And this lamp you can see here is a U-tube. Inside you have a sodium, and you have also some neon. This lamp when switch on, initially they are red, and then the sodium heat up, and you see the yellow light coming. It's completely yellow, no color under index, very low correlate light temperature. You need a lot of time to warm up, 15 to 20 minutes. That means in the highways, they had to switch on the lamps at least half hour before the sundowning, in order to be sure that we have enough light. And they operate only in horizontal position. If you put it vertical or in the other side, you will destroy the lamp. Well, they are used mainly for highway lighting and for tunnel lighting, but now they are obsolete and banned. No one produce anymore this kind of lamps, and of course they are not recyclable, but you don't have lamps like that at home. If you want to put a lamp like that at home, you have seen the movie The Addams Family. If you are part of the Addams Family, you will love those kind of lamps, because you will have a completely cadaveric, dead appearance under the light of those lamps. Well, what we used end of 80s, end of 70s in our cities was the high pressure mercury lamp, or high intensity discharges. You see the lamp is here inside. You have an external bulb to protect. And here inside, when the lamp is switched on, the operating pressure inside the bulb is around between 1 and 5 bars. When the lamp is switched off, the pressure inside the burner is less than, is around 20 torrs. It's very small, okay? When the lamp switches on, you have a mercury discharge inside, producing mercury lines, very poor spectrum. Powers you can go up to 400 watts. We use essentially for city lighting, very low efficacy, bad CRI, unpleasant color temperatures, at huge lifetime also, up to 20,000 hours. This kind of lamp you can find maybe yet in some remote areas, in villages that they install such bulbs in 80s, 90s, and the lamps, they are still there. They are switched on. They don't produce a lot of light, but they are still on. They need 10 minutes to warm up, and 5 to 7 minutes to start up. They don't like hot strike. If they switch off accidentally, you have to wait maybe 5 to 10 minutes before being able to switch the lamp again on. Contains a lot of mercury, up to 250 milligrams of mercury per lamp, and can operate in any position. This is not a problem. And again, obsolete, banned, and not put on the bins. High pressure sodium lamps, this is still alive. We can find still in our cities, less and less. This is the yellow lamps that you have to eliminate outside. Here, this is the lamp, is the stick that you see inside. This is the burner, but the burner here is made by alumina. Why alumina? Or the more common name of alumina is sapphire, but not sapphire for making precious stones. It's just oxide of aluminium. Why? Because sodium, when it is in liquid state, it is very aggressive for quartz, for glass, or for silica. It will drill the silica and will leak, and the lamp will destroy very rapidly. But alumina is not sensitive to that effect, or say that the effect is much slower. Well, this lamp emits yellow light. You can see here we can go up to 1000 watt. 1000 watt is not used for city lighting. It's used for greenhouse lighting. Efficiency, rather good, 130 lumen per watt, but low CRI, low color temperatures, honest lifespans, good startup time, no hot restart, and universal operating position. But this lamp is not obsolete, but it is banned because it contains also mercury. Not put on the bin, and if you have many of those lamps in some area, you have to declare that to the fire department. Because if there is fire, if the lamp cracks, inside there is metallic sodium. And sodium, if you put water, it burns. Well, fire department has to know, don't put water in that room because they are stock of sodium lamps. You can make the experiment. You take one lamp, you get out the external bulb, you crack the lamp, and if you put it in a bucket with water, you may have flames coming out. White light, yellow light is not good. We try to find a solution to get white light. That was the mercury metal halide lamps with a quartz burner with very good characteristics, used for outdoor and sodium lighting, because you can go sodium light, you can go to high wattages. But big problem, they contain not only sodium, they contain all heavy metals that in liquid situation they also drill the quartz, and the lamp stability and lifespan was very small. And then the next idea was to replace the silica burner with a ceramic burner with alumina, like in sodium lamp. And this one has better resistance, and you can see very large spectrum. That means excellent color rendering. You can make any color temperature. It depends what you put inside. You want to have more blue, you put a little bit more indium or calcium. You want to put more green, you put more thallium. You want to put to get more red, you put more strontium, and things like that. The chemistry inside that lamps is extremely complicated, and we are speaking about very high temperature chemistry, because the temperature inside the burner can go up to 7,000 Kelvin in the center, and in the wall is around 1,200 degrees C. Okay, in one centimeter thing. Huge technology to develop such lamps. They are still used for public lighting, for large space, and also horticultural lighting. But unfortunately, they have to be banned because they contain mercury. But these lamps, they have the largest exemption period. They can go up to 5 years. That means beginning of next decade, we'll continue finding such kind of lamps in our home. And this was the lamp that we developed in the frame of the European project, who demonstrate the mesopic vision problem has been developed between us and General Electric. And this lamp, we play with a chemistry. If you reduce the power by 2, you increase the blue part of the spectrum, and you reduce the red part of the spectrum. That means you have more perceivable light, even if you have 2 times less power inside. Yes, that's all about this kind of lamps. And then this afternoon we'll speak about LEDs and organic LEDs, which is maybe unknown animals for you, but it's very interesting to know what is that. Questions? Yes. The CFLs use mainly halophosphates. Don't ask me what is the exact chemical formulation of halophosphates. You can look that. And they are doped with cerium as an activator or some other earths. Usually they are the best phosphors. They are yttrium oxide doped with either europium or cerium or gadolinium. You can find all of them. That means these lamps, they contain rare earth materials in rather high density that you need to recover after. The halophosphates, they have just europium, which is less critical. The halogen lamps, well, the halogen lamps has been gone also. You speak about halogen or halide lamps. Halogen is an incandescent lamp. The only thing that you put inside the bulb instead of nitrogen, which is a neutral gas, you put inside oxybromide of iodine, which is a molecule that dissociate when you are in temperatures higher than 1000 degrees. That means when you are nearby the filament is at 2000 something, the molecule dissociate and you have bromine, free bromine inside the lamp, and the molecule will reassociate near the bulb when the temperature will be lower. But what happens when you have free bromide? If your filament is vaporizing, is tungsten, the bromine has a very big chemical affinity with tungsten. Well, a tungsten atom come out from the filament and bromine is nearby, catch it, and then as you don't have any bromide tungsten atoms on the filament because the temperature is very high, you have a difference of density of bromide tungsten atoms nearby the filament and the filament. That means by diffusion, the bromide atoms with tungsten will go on the filament and then they will dissociate. The tungsten will stay in the filament and the bromide will come back free to catch another atom. That means you can get the vaporization, vaporized tungsten. You can get it and collect and get it back to the filament, and this allows you to send a little bit more current in the lamp and have higher efficacy. And also the most important fact is you can make smaller lamps because the tungsten usually goes to the wall and the wall becomes black and you lost light. By getting the tungsten back to the filament, you avoid the blackening of the walls and you can have smaller lamps with higher lifespan. And you know very well this kind of lamps, which is linears very often, when they finally are dead, you have almost an explosion inside and you see that the tube is completely black because then the system is no more working. Bromine cannot catch all those tungsten atoms. The filament is breaking and all the tungsten atoms are on the wall and the wall is completely black. Okay, this is it allows to pass a little bit more current and shrink the dimensions of the lamp. Without bromine you cannot do it. But this lamp is also banned, and the last evolution was the high efficacy. Was exactly this principle, but behind you had an AC-DC converter, and you make the lamp operating at DC low voltage in order to avoid some undesirable effects with very high vaporization rate and things like that. But the lamp was very expensive, and the lifetime was lower than 1,000 hours, and that was intentional. Why intentional? Because those lamps has been proposed as transition lamps between the incandescent and the new generation of CFLs and LEDs, and the idea was, let's put on the market lamps when the end user will buy it, will replace so often, and at the end it will say, never seen that kind of lamps, I will go with a new one. It's a commercial strategy. Yeah. Yeah. Well, the quality of light is much more complicated than that. The quality of light has nothing to do with the efficacy. The efficacy has to do with energetics. The quality of life is the color rendering, how well you can see the colors, and the color temperature, because the color temperature, I will explain that later, depends, can change your circadian rhythm, can change the secretion of some hormones inside your organism. It depends what you want to do. And then you have also other parameters, which is the quantity of light, the directivity of light, and the quality of light is linked to all those parameters, but not in the efficacy. The efficacy is just energetic quality. Okay? We don't have today a single measure for light quality. We are in obligation to speak about different parameters. My dream is not to catch the lightning and put in a box, but is to have a single merit figure for designing the light quality. But it's very complicated. Okay? The CCT is linked to the ambience, is linked to our well-being. I agree that up to now you cannot understand that. You will see that later, and you will understand. Any other question? Okay, then it's time. We can. Yeah, it's 1:30 and 3 o'clock. Yes, we recombine at 3 o'clock. 1 hour or 1 hour and a half. I will speak to you about LEDs, and I will make some demonstration also how LEDs work. Okay, well.